In today's class, we will learn about Faraday's law of electromagnetic induction. First of all, we will see what is electromagnetic induction. So, we have studied that when an electric current passes through a conductor, or for example a solenoid, when an electric current passes through a solenoid, it sets up a magnetic field. So, when an electric current passes through a conductor, a magnetic field is set up. That means we can convert electric energy to magnetic energy. Electric current passes through a conductor, it produces a magnetic field. Around the conductor. Therefore, we can say that magnetism can be created by means of electric current. We can create magnetism. Magnetism can be created by means of an electric current. Now, what happens to the converse? If we have an alternating magnetic field, or if we have changed the magnetic field, can we produce electric current? The converse of this, that means electricity can be created by magnetism. That is also true. But how can we do that? Magnetism can be created by means of electric current. So, can we produce electric current using magnetic field? The converse. So, electric or electricity. You can write electricity. Electricity can be created by magnetism. But how? Electricity can be created by magnetism, but how? So, for that we require a magnetic flux which is changing with respect to time, or we require a change in magnetic flux linking with the conductor. This can be obtained by changing the magnetic flux linking with the conductor. Linking with the conductor. The flux which passes through this coil must change, and this process is called as electromagnetic induction. So, creation of electricity using magnetism by changing magnetic flux linking the coil is known as electromagnetic induction. This process is known as electromagnetic induction. Now, the Faraday conducted some experiment to prove this. He showed how we can produce electricity using magnetic field, and can we increase or decrease the magnitude of electric current or EMF. He observed all these by conducting experiments. Now, due to this electromagnetic induction, an EMF is produced in the conductor, and that EMF produced is called as induced EMF, and the resulting current is, we can call it as induced current. So, the main important thing here we need is change in flux linking the coil to produce EMF, which is called as induced EMF. And if you close the circuit, a current will start flowing, and that current can be called as induced current. To do these things, using magnetism or using a magnetic field, we mainly want change in flux linking with the circuit. Change in flux linking the circuit. Now let us see how Faraday did experiment. So experiment 1. How can we do this, or how can we demonstrate this? Experiment 1. Now take a coil. Okay, so let us take a coil. And a galvanometer is connected to the coil to see the deflection. Coil was taken, and then a magnet was moved near the coil and away from the coil. Magnet, and this is a coil. A magnet was moved relative to a coil. The coil here is stationary and a magnet was moved. When the magnet is moved away from the coil or towards the coil, the galvanometer showed some deflection. That indicates that there is an induced current. Now, what all things we can observe from this? So the first thing is, so he observed these things. If a magnet is moved towards the coil, the galvanometer showed some deflection. Magnet is moved towards the coil, galvanometer showed some deflection. If a magnet is moved towards the coil, so here, sorry, if a magnet is moved towards the coil, galvanometer showed deflection. Now, and this deflection indicates that there is an induced EMF and hence there is an induced current. Now, if the moment of the magnet is stopped, there was no deflection. That means that when the flux linking the coil changes, then only we have an induced EMF and induced current. And when the magnet was stopped, there was no deflection. That means that the induced EMF or the induced current is 0. And he also kept the magnet stationary and moved the coil. Then also the galvanometer showed some deflection. That means that either you can move the magnet or the coil, and hence we can conclude that when there is a relative motion between the magnet and the coil, there gets an EMF induced, and hence if the circuit is closed, there will be a induced current also. Let me explain you once again. The magnet was moved towards the coil. When the magnet was moved towards the coil, what happens? The flux which links this coil keeps changing, and when flux linking the coil changes, the galvanometer shows deflection. If a magnet is moved towards the coil, galvanometer shows deflection. And the second point you can write, when the magnet was stopped, no deflection. Also, if the magnet was stopped and the coil was moved, then also there was a deflection. Magnet kept stationary. Magnet kept stationary. Coil is moved. In the magnet kept stationary and the coil is moved, then also there is a deflection. G shows deflection. Different cases. The case 1 is magnet is moved towards the coil or away from the coil. Then there is a deflection. When the magnet is stopped, there is no deflection. When the magnet is kept stationary and the coil is moved, then also G showed deflection. So by this we can conclude that whenever the flux linking a conductor changes, an EMF is induced in it. Whenever the flux linking the coil changes, an EMF is induced. Okay. Now it has been also observed that when the magnet is moved towards the coil, the galvanometer shows deflection towards one side. If the magnet is moved away from the coil, then the deflection is towards the other side. That means, the direction of current gets reversed when the magnet is moved away from the coil. So we can conclude that the direction of the induced EMF depends upon the direction of magnetic flux. So next I will write, the direction of the induced EMF depends upon the direction of the magnetic flux. Direction of the flux. This can be observed by moving the magnet towards the coil and away from the coil. When it is moved towards the coil, the deflection was towards to one side, and when it is moved away from it, the deflection was in the opposite direction. And the third point, we can say that the speed with which the magnet was moved. So if the speed was increased, the deflection was more, indicating that there was a greater EMF induced and hence there was a greater current. If the speed was reduced, the deflection was less. That means that the induced EMF is less. So magnitude of the induced EMF depends upon the rate of change of flux linking the conductor. So magnet moved away or towards coil with speed, greater speed. Magnet moved away or towards the coil, I will just write, with increased speed. Increased speed. I am not writing the correct sentence, I am just writing the sequence. The magnet was moved away or towards the coil with increased speed, then the deflection was more. More deflection. So increase in speed means more deflection. Now magnet moved away or towards the coil with decreased speed, less deflection. That means that the induced EMF or the magnitude of the induced EMF depends upon the rate of change of flux linking the coil. We can conclude that the magnitude of the induced EMF depends upon the rate of change of flux linking the coil. From these things which the Faraday observed by conducting the experiments, he came with laws of electromagnetic induction. So in the next class I will give you the statement of Faraday's law of electromagnetic induction. There are two laws, first law and second law, and there is another law, Lenz's law, which will give us the direction of induced EMF, because we said when the magnet was moved towards the coil, the deflection was towards one side, and when the magnet was moved away from the coil, the deflection was towards to another side or the opposite side, which means that there is some direction for the induced current. Lenz's law gives the direction of induced EMF. These things will continue in the next class.